All right, everybody, welcome to Earth Science. Let's get ready for our final test and the first classwork of marking period 2. So what I got here is 10 pages, which sounds like a lot, but I spaced it out to make it kind of hopefully intuitive. So each page will have one important idea and one question. And then what you'll do is take these questions and do them in a Google form like quiz. And I think all I'm going to do for that, so that I don't have to retype all this stuff, is just write question 1, and then your choices will be 1, 2, 3, 4. So you'll have to look at the question here, but then answer in the Google form. Hopefully that works out. If not, I apologize. Let's do it. Gravity is dependent on mass and distance. A mass over the two objects, how close together are they? I'm gravitationally attracted to this pool ball. It and my head are gravitationally attracted to each other. We have mass. There's a distance between them. The further away they go, the less gravitational attraction there is. The more mass, the more gravitational attraction there is. So you need something huge to really be able to feel that force, like this planet, which is why we're all stuck to it. So the closer an object is, the higher the force of gravity. That stuff was really on the last test, but here's where it comes into play. Therefore, the moon has a large effect on our tides, and the sun has a small effect on our tides. Uh, Closer. The sun's a lot bigger, but the moon's a lot closer. But when we get down to spring and neap tides down here, that idea is gonna be important. So try question number 1. Check it in the Google form. All right, tides. Tides are caused by the from the moon. That gives us these tidal bulges. And this is simplified. This is like what if you go to college and study this, you're going to find out it's a lot more complicated. But because the moon's gravity is yanking here, it gives us this. And then because of the way there's some complicated physics to give us another tidal bulge over on this side. Thankfully, we don't have to fight through that in this course. But then since the Earth spins through both of those bulges, we end up getting about a high, a low, a high, and a low every day. Now, since everything else is moving at the same time, it takes about ballpark 12.5 hours, a little bit less maybe. Meaning just to go from high to low is about 6.25 hours, like a half a cycle, right? So yeah, about 12 hours and 20 minutes maybe is usually what they are, but it can vary with spring neap, shape of your coastline, all kinds of things can lead to changes there. So there you go. There's number 2. Try question 2. Throw it in the Google form. All right. Since the moon has a larger effect on our tides, and the sun has a smaller effect on our tides, depending on the moon phases, the tides are either larger range or smaller range. You really want to avoid saying the tides are higher during this thing, because the high tides are higher, but the low tides are lower. So what you want to look for is this idea of range. Now this is exactly copied out of your lab, so if that was making sense to you back then you're in good shape. But this is like high highs down to low lows. That's a large range, and that's going to be a convoluted arrow here. That's going to be what we have in spring tides right there. Large range versus what doesn't go as high, doesn't go as low. So this blue line is the high and the low every day. How much is going up and down? Here it's not going up and down quite as much. That's going to be what we call a neap tide during the first and third quarter, and that's going to be line there. So it's like the other one, a small range. So you can see the range goes like up, then down, then up, then down, then up. And yeah, there's like some difference between this large range and this large range. But that's okay. If it's getting larger, spring tide. If it's getting smaller, neap tide. And those moon phases match it. I really recommend watching this video. If you were in class on the one day I showed it, some of you might have seen it, but like watch it and watch it and watch it. It's like 30 seconds long. Watch it a bunch of times. You'll see the pattern. All right, a couple easy ones for 4 and 5. Earth spins on our axis. It's important to keep this difference down. We call this rotation. We'll do revolution for number 5, but keeping that difference between rotation and revolution is important. It gives us our days, and like above it does, yeah, it gives us tides too, but we'll just worry about days right now. It makes it look like the stars and the sun, the star, are moving. Well, throughout the course of the day, they'll move. Why does the sun go across our sky? It's not because it's actually doing that, it's because we're spinning underneath it. And the important piece of evidence, this is one of those like relatively straightforward questions. FOUCAULT. That's the thing. And again, if you hopefully you've been tuned in, if you watch the video of me making a fake one of these on my kid's swing set with his Halloween bucket, the idea is that you get this thing swinging, and it will throughout the course of the day you can see it's knocked over these pegs. Throughout the course of the day, it'll basically shift its way around the room, providing strong evidence for Earth's rotation. What about revolution? This gives us what we know as years, and is also responsible for the seasons. Makes it look like, I don't know if I mean, it's kind of weak. Don't worry about that a whole lot. But it is what really is our important piece of evidence. In May, if you wanted to see Aries, you'd have to look through the sun. In other words, it's daytime and it's on the back of the sun. You're not seeing it. So if you wait till 6 months later, now you can see Aries. Whereas if you wanted to see Libra, you'd have to look through the sun. So it gives us seasonal constellations. I spelled that right. For some reason the question is missing there, so I'm going to find that question and stick it back in there. I don't know what happened there. Yeah, so that's our evidence for Earth's revolution. There'll be a question that matches that there in a minute. I don't know where it went. All right, latitude on Earth. Those numbers that we have for latitude, we're like in the mid 40s, are based on the altitude of Polaris. All right, so keep it simple. Your altitude in the northern hemisphere, it's all it is equal to the altitude Polaris. So this dude right here, I mean, if I'm doing the Tierra Polaris guy, I'm going to point that way. That way is north. That wall is north. Like, you guys know where the road is over there. North lot, south lot, right? That's north. We're at about 43 degrees latitude. That means if I want to point at Polaris, I got to point up at 43 degrees. If that angle right there is 43 degrees, I'm pointing at Polaris. I know it's there. It's light outside. There's a ceiling in my way, but I know I'm pointing at, because those two numbers are the same thing. It's how they designed latitude. So this dude right here is looking up at that angle of 66.5 degrees to see the North Star, Polaris. Therefore, his latitude, 66.5 degrees north. Only works in the northern hemisphere. Okay. If you were to do this, is like a time lapse photo. If you were to leave the shutter of a camera open for a while, Polaris is right in the middle. And all the other stars then spin around it, and again appear to spin because it's really the Earth moving. This is like if you can picture yourself on a ride at the fair. As it spins, it looks like everything else is moving. If you picture yourself sitting still on that ride, everything else is moving around you, right? So they'll call those, no, not the eraser, circumpolar stars. And in just a minute, we're going to figure out how fast they're moving. Please don't get these questions wrong. These are like the freebies. All right, how quickly does the Earth rotate? So, got to know this, and you got to know it in degrees per hour. This is a memorization number. This is not the reference tables. Now, if you're not good at memorizing things the way that I was not, just think about it when you get there. The Earth has to spin a full circle. We all know that a full circle is 360 degrees. And we have to know that it does that. We all knew both of these things. You knew this, that a day is 24 hours long. So you hit some calculator buttons and it's going to tell you that the Earth is rotating at 15 degrees per hour. Therefore, the stars, I'll be lazy here and just draw arrows, move at 15 degrees per hour. And the sun moves at 15 degrees per hour. All of that stuff happens because of our spin. All right, so the regions will occasionally ask, like this one, will ask you to just do some very light math with it, like how far does the sun move in 2 hours? So if it moves 50 degrees every hour, in 2 hours, it moves 30 degrees. Or if you had to do it the other way, how long does it take the sun to move 45 degrees? Well, it does 15 degrees every hour, so 15, 30, 45 would be 3 hours. And this is an example of figuring that out. You guys got it. Important idea number 8. Since the Earth has 360 degrees of longitude, and we spin through them all every 24 hours. Once we could travel fast enough, we needed standardized time. So we invented time zones. Orange all the way around the planet. 1 hour for or one segment for each of the 24 hours of the day. And then really the idea is that longitude is based on time, these longitudes. So if you are on this dotted line right here, which doesn't quite hit us, it goes through the Adirondacks, everybody on that dotted line has the same exact solar noon, the same exact sunrise, the same exact sunset. And as you progress west or east, that changes. But longitudes go with time. Earth is moving that way. The East Coast is like the bumper of the car. We get the first sunrises. So whatever the time is here, it's 8:05 right now. Let's just pretend it's 8. So it's 8 a.m. here on the 16th of November. It's 7 out there for Central Time Zone. It's 6 out there for the Mountain Time Zone, and it's 5 in the morning way out west. They have not gotten their sunrise yet. Right? We barely have. All right, that's how that works. Do it. All right, I'm not going to go through all the moon phases again because we're short on time here. And but you got to study this up. This is going to be one of those that's like it's coming. You know, it's coming. Study up. Half the moon is lit every day, which is why these ones here on this ring are half lit every day with the light half facing the sun. Phases are what portion of the lit half do we see? And again, the hard part to this is saying this image is from out in space. But when you look like from the Earth out to here, you see only the light side. So that's a full moon. When you look from the Earth over to here, you see only the dark side. That's a new moon. And all the phases in between, you know, it's common. Study those up, get them down. You don't have to memorize them if you can really think your way through. You can do it. One orbit is 27.3 days. Oh, look at that. 7.3. One cycle of phases. And that's in the reference tables, that first number. This one is not. 29.5 days. And it's that whole idea. Let's see, cheat sheet number 3, if you're stumped on that. That the moon needs an extra 2.2 days to catch up to the revolving Earth. Waxing is filling with light. In other words, from new to full, light on right. Meaning is emptying light. In other words, from full back to new, light on left. Want to know the biggest problem to this question historically in the past? 2-week period. What works for a 2-week period? All right, seasons. There's a lot to do here. Bell's going to ring here in like 2 minutes, so we got to kind of move forward. I mean, I'm not going to make you do that whole entire chart again. We've done it twice, but be able to spot over here is winter because the axis is leaning back away from the sun. Our latitude gets it indirectly and has mostly dark. So the day that would be like the first day and the day where we're leaning the most away from the sun is 12:21. The axis tilt is 23.5. Don't forget that. Here we go, leaning towards the sun, so we're getting more direct sunlight and we're getting long days at 6:21. And here the sun would like directly hit down at the Tropic of Capricorn, 23.5 degrees south. Here it would hit at the Tropic of Cancer, 23.5 degrees north. And then the two equinoxes where everything equals out. Everybody gets about 12 hours of daylight, 12 hours of darkness. They pretty much function the same. It's just that this one's after summer. It tends to be on the 23rd, but if you say anything in the low 20s, the Regents is always pretty kind to you on that. 3:21. All right, so most sunlight, least sunlight, 12 and 12. All right. It's a lot, folks. It's a big one. And then one more question. So again, I'll set up this question, this Google form, whatever it is, the classwork quiz, but you'll just have to be like, this is question one. You read it here. You say, my answer is this. You just plug that into this thing. Deal? There's the bell. Here you come. Thanks a lot. We'll catch you guys soon. Stop this video.